You know the AI that's suddenly everywhere? The kind that can translate a language in a split second or that knows exactly what movie you want to watch next? Well, have you ever stopped to wonder how it actually works? The answer, and this might surprise you, has its roots in physics. So much so that it just won the 2024 Nobel Prize in Physics. Okay, let's get into this. It's a wild story.
So, the big question, the one at the heart of all this, is how does a computer actually learn? I mean, we're not talking about just calculating things. Computers have been amazing at that for decades. We're talking about learning from experience, kind of like how you and I do. And believe me, there is a world of difference.
Think about it like this. Old school software is basically a recipe for a cake. You give it the data, that's the ingredients, and you give it a super strict step-by-step set of instructions. Follow the recipe, you get a cake. Simple. But machine learning, that's way more like a little kid learning what a cat is. You don't give the kid a rule book for cat. You just show them examples. Look, that's a cat. Oh, and that one's a cat too. After a while, they just get it. They figure out the pattern of catness all on their own.
And that, figuring out the pattern, is exactly where our Nobel laureates John Hopfield and Geoffrey Hinton come into the picture. Way back in the 1980s, their work laid the groundwork for this totally new way of thinking about computing, a way for machines to finally find those patterns for themselves.
The Royal Swedish Academy of Sciences gave them the prize for, and I'm quoting here, foundational discoveries and inventions that enable machine learning with artificial neural networks. Now, the key word there is foundational. They didn't just make computers a little bit better, they gave them a brand new skill. And their big idea, the secret sauce that brought the entire field of AI back to life, was to look somewhere totally unexpected. They decided to borrow tools and concepts from physics. Yeah, they applied the laws that govern the physical world to the problem of processing information.
All right, so let's break this down. We'll start with John Hopfield and the whole challenge of memory. How do you build a system that doesn't just store something, but can actually recall it, even if you only give it a messy, incomplete clue? What he built is called an associative memory. You know that feeling when a word is on the tip of your tongue? You remember the first letter, maybe how many syllables it has, and your brain just starts churning through possibilities until, pop, it finds the word. That's exactly the kind of memory Hopfield wanted to build inside a machine.
And his inspiration for this was just brilliant. It came from the physics of magnets. He looked at how all these tiny little atomic spins inside a magnetic material all talk to each other and line up to create one stable magnetic field. He thought, hey, maybe the connections in a network could work together just like that to remember a stable pattern.
He came up with this amazing analogy, the energy landscape. Picture a hilly landscape with lots of valleys. Now, you give the network a fuzzy, distorted picture. That's like placing a ball on one of the hills. The network then just lets go. The ball starts rolling downhill, all on its own, always looking for the lowest possible point. And when that ball settles at the very bottom of the valley, that's it. That's the memory. The network has found the cleanest, most stable version of the pattern you were looking for.
Okay, so that's Hopfield's breakthrough on memory. Now let's turn to Geoffrey Hinton, because he tackled the next massive problem. It's great if a machine can recall things it's already seen, but how can it possibly recognize something completely new?
Right, we're back to our kid learning about cats. After you show them a few cats, they can go to a friend's house, see a totally different kind of cat they've never seen before, and still go, hey, a cat! How do you give a machine that kind of flexible, abstract understanding?
Hinton's answer was something called the Boltzmann machine. And surprise, surprise, it was also inspired by physics from the 1800s. Now, this machine takes in data through what he called visible nodes, but the real genius was in its hidden nodes. These hidden nodes are the magic. They're not told what to do, they just work behind the scenes, figuring out the deep, essential features of the data, that abstract catness. Once the hidden nodes learn that pattern, the machine can spot a cat it's never laid eyes on before.
So, you have these incredible, powerful ideas from the 80s. They were the seeds. But how do we get from those early theoretical models to the mind-blowing AI that's literally changing our world today?
Well, you have to remember, their work came at a crucial time. AI research had gone through this period called the AI winter, where a lot of people just gave up on the idea of neural networks. Hopfield and Hinton's physics-based approaches completely reignited the field. They set the stage for the absolute explosion that kicked off around 2010, which is when we finally had two things they didn't: massive amounts of data and insane amounts of computing power.
And when I say an explosion in scale, it is almost impossible to get your head around the numbers. Let me try to put this into perspective for you.
So back in 1982, the groundbreaking network that Hopfield described in his paper, the one that was considered really complex and powerful for its time,
It was built with
30 nodes. That's it, 30. He even wrote in his paper that trying to simulate a network with 100 nodes was just too much for the computers back then.
Okay, now, flash forward to today. The large language models that we use every single day, these networks are built with
over 1 trillion parameters. I mean, just think about that. We didn't go from 30 to 1,000 or 30 to 1,000,000. We went from 30 to 1 trillion. That leap is just astronomical. But it's a direct line, from their foundational ideas to where we are now.
And with that kind of incredible power, you can do some truly amazing things. It goes way beyond just translating languages and recommending movies. This tech is now on the absolute cutting edge of science. It's helping us discover things like the Higgs particle, finding planets orbiting other stars, analyzing gravitational waves, and even designing brand new materials for things like solar cells.
So in the end, what Hopfield and Hinton really did was fundamentally change the conversation we have with computers. We stopped giving them strict recipes to follow and started giving them experiences to learn from. It was a total game changer.
And hey, don't just take my word for it. The Nobel Committee itself says it. Machine learning development has exploded, and it's all built on that core idea of the artificial neural network that these two laureates helped bring into the world. Which, of course, leaves us with a really fascinating and maybe the most important question for our future. We've built these incredible machines that are just astoundingly good at finding patterns. So the real question now is, what patterns should we show them? Because whatever data we choose to feed them, whatever we ask them to learn, that's going to shape all of our futures. Definitely something to think about.